Hello everyone, welcome back to the power system, class 19. In this class, we're going to talk about two things. Even in class 17 and 18, we learned about optimization techniques, right? In this class, we're going to apply those techniques to the power system. So we're going to do two things here. The first part of the video, I'm going to talk about economic dispersed neglecting losses, so no losses, and no generation limit. So your power gen doesn't have a limit and you have no losses. Then second video I'm talking about neglecting losses still, but we're gonna put limit to the generation. Right? That's the goal for this lecture. Let's get started here. In power system, your fuel input, like what kind of fuel is coming in, and what is the power output of the generator can be described by a quadratic function. All right, and same here, your fuel cost, how much is cost per hour, fuel cost per hour, can be draw against the power output by using kind of quadratic function. So to that here, now for both function over here, so let's say talk about this guy over here. PI, how do you describe PI, right? So the relation between the cost and power of a particular generator is alpha I, beta I, pi plus gamma I pi squared. So alpha, beta, gamma, those are the constant depending on so many things, in depending on fuel coming in, depending on efficiency, depending on a process, all those goes into the constant. So, and Ci is the cost. So now if I take a derivative of Ci with respect to Pi, this becomes this, right? This is called incremental fuel cost. So that's, and if you draw that incremental fuel cost with the power output is becomes a linear curve. So it's dollar per megawatt hour. So if we want to increase megawatt hour power input from a power plant, how much going to cost? That's the incremental fuel cost. Like over here, this is the power output, this is the cost here. If you're going to come over here for this increment, how much is going to cost? So that will tell you that this is what your lambda I will tell you what the incremental fuel cost. All right. So this is it's a linear function. So if you want to go one stage of power generation to the next stage of power generation, how much is going to cost? That would be given by the incremental fuel cost, and this is the equation right here. Right. Okay. So let's put it together to the optimization technique. Let's say you have multiple power plant, right? These are multiple power plant over here. Each of them has their own cost function, right? And each of them have their own output over here, and you're trying to satisfy a demand. So in a lossless system, your demand should be equal to your generation. So PD should be equal to your PG, right? All right, now if you have multiple cost function, you can add all of them to find the total cost function over here. So, and you can use this equation over here. I could go from 1 to n could be any number of your generating plant. And constraint is here, this equity constraint is here, is that your PI, all the generation should be equal to your demand, right? So this also can be written as PD minus number of generating plant over here, I equal to 1, Pi should be equal to 0, right? So that is your also your equity constraint. All right. So now, as you know that Lagrange multiplier and Lagrange function over here, new function over here, that's your this is Lagrange multiplier over here. This is the equity constraint, and that's the function you're trying to optimize, right? So now, if you take the forget about this one for now here. If I take the partial derivative with respect to Pi, this becomes this function, right? Right. So then your this function over here is there's it is your let's see over here. The CT is you add all of them, you get the CT, and if you do one by one, dCi by dPi also is lambda, right? That's what you have seen before. So then Ci could be any power plant, and this is your equation for that power plant, right? You have seen this equation, last slide right here, right here, oh no, before that, right here. That same equation, right? So from this one over here, you can also you can find the pi over here to be beta I minus lambda over 2 gamma I, right? You can also find that from that equation. Okay. So now, for the second one over here, the second function over here, if I do this, all right, and apply that, that will to the equation we have over here, this equation over here. So this becomes 0, and the lambda is a derivative, so we only left with this portion over here, only this portion over here. That is, and you can rearrange that with that right here. Okay. So now, as I said, the previous pi could be this equation, as I said in the last slide. Then you can put this this equation and this equation together to get this equation over here, right? So with that, now you can solve for lambda over here. If you want to solve for lambda over here, that would be this equation over here. So if you solve for lambda, that becomes that equation right there. So that's the lambda. So now for neglecting losses, if you don't have no losses, your equation could be solved by analytically. But when you have loss in there, you need to solve it by iterative process we learned before. So I'm going to show you both here. So let's show you analytical process. You know how to solve it. Let me show you how to do it with the iterative process. So this is the equation we just saw right here, right here. So I'm going to brought this equation back here, right? So this is my f lambda equal to d. That's my equation, right? So now, if I use Taylor series, as you know that, if I use Taylor series, I'm going to come with this, right? My C is PD now. C is my PD over here, right? So the lambda, delta lambda k would be this equation over here. As you know that this is the difference between your C minus F lambda, which is so lambda right here. So this is your delta pk, that is the difference between C minus F lambda, which is PD minus F lambda here. So that is right here, okay? And this is the first derivative of the function f right here, right here. So that is right here, okay? So now, if I go further into the equation over here, it will become this one. Why? Let me tell you why. Your f is ng I equal to 1 beta I to lambda I, right? If you take the first derivative with respect to lambda, right? So this becomes 1, right? This becomes 0, and this is your coefficient. That's right here. Can you see that? So it's right there. So that if you take that one, that becomes right here. Okay. So that's your basically your lambda delta lambda k. And once you found this one here, you add that to your estimate. You find the next step. And go on. That's how you go forward. This is the successive process here. This is the successive process here, right? So goal is that you have to find delta lambda k and use that to find next step and go process until you your function, this one here, is meet your threshold. It could be 0, could be a little bit bigger than 0. What is this? Is the mismatch. This is the mismatch between your generation and the demand. So your mismatch is 0. If perfect is not 0, like I said, you have mismatch is 0.001. You can still live with that. All right. So now let's apply that to a power system. Here I have 3 power plant. My cost function is given for all 3 of them, C1, C2, C3. And you know that this is the alpha, this is the beta, this is your gamma. So it's alpha 1, beta 1, gamma 1, and so on. So first of all, what I need to do here, I need to let's solve it for analytical method, then we will solve with the graphical method. That's graphical method, then we'll solve with the iterative process. Okay. So first of all, for the for the what do you call it, analytical method, I have to find lambda here. So this is the equation for lambda. So that lambda is takes everything over here, so you can put all for all three of them, and you find the lambda. This is the lambda you want. This is the increment of cost per megawatt hour. So now with that, I can find how much I need to find from the power plant 1, 2, and 3. So if I do that, my cost would be minimized. All right. So that's the analytical method over here. Now let's go to graphical method. If I plot them, if I plot these three functions with the MATLAB plot function, you can see that all intersect at this point over here. At that point, I have 400, 250, and 150 for all the generation. Okay. Okay. Now, for gradient or iterative method, all right. So here's the thing. So you know that P1, P2, and P3. You know all those equation over here. So P1 or like the Pi over here is lambda minus lambda I over 2 times beta, it's a gamma, right? Gamma I, right? So that equation, if I put over here, my initial estimate, this is my estimate, this is my estimation assumption, 6 with the 6 over here, so I can found that P1, P2, P3 generation from power 1, power 2, power 3. But if I try to match with my demand 800 megawatt, I see that I'm way off, right? That means my gamma is not there yet. So I'm gonna find the first delta lambda 1, delta lambda 1 is in the equation. That will give me the 2.5. So I'm going to add this. I'm going to add this one to my the estimate value to find the next one. So here my estimate value and the difference delta gamma for the next one. And with that one, if I go back again, I see that I have all those power generation over here, and they match perfectly. That means my delta P is 0. That means it's perfect match. So now I know that how much I need to generate from each of the power plant, right? So that's how you. So now if you go back and look at the total cost, look at the total cost here. So generating that much, I'm getting that much cost per hour. Okay, so that is the optimal or minimum cost. All right, that's how you do the optimization. It is a simple technique. There's a more advanced, more complex technique out there to solve the optimization problem. So next one we're gonna solve about how you put the limit on generation, what will happen. All right.